The Earth System, a video series for educational institutions for free use presented by the German Geological Society, the DGGV. Hello everyone, I welcome the viewers of another episode of my video series on the Earth System. In this video, I would like to discuss the geometry of plate movements, particularly by looking at a sphere on which these movements take place. This is of fundamental importance for plate tectonics because it entails geometric constraints that we can clearly see in the plates and especially in their boundaries. This is what I would like to explain here. A consequence of the Earth's spherical shape is that all plates on Earth together form a closed system. We can see it here in this illustration. There is no gap between two plates, and yet all the plates move towards, away from, or past each other in very different ways. And the system has to remain closed because a hole must not appear anywhere. The great thing is, the three different types of plate boundaries that we have are actually sufficient for this. Divergent plate boundaries, where spreading occurs at the mid-oceanic ridge, convergent plate boundaries with a subduction zone or when two plates collide, and conservative plate boundaries with transform faults. We know that new oceanic lithosphere is formed at spreading zones. Two plates move apart, and the gap that opens up between them is filled immediately with new oceanic crust or lithosphere, as I have already explained in detail in previous videos. But this only works if something is removed at the same time from another place on the globe, because if that didn't happen, the globe would become bigger and bigger. There would no longer be a closed system. But it is not possible because we are not gaining any mass. The Earth solves this problem with subduction zones. There, oceanic lithosphere is returned into the Earth's mantle, and because we are on a sphere, we can assume that exactly the same amount of lithosphere that is formed in spreading zones worldwide is removed in the subduction zones. And I would like to remind you that everything only happens because the heat from the Earth's interior has to be pushed outwards. In any case, the geometry behind plate tectonics means that we always have to be aware that the thin lithospheric plates move on a large sphere. And this results in the geometric relationships that the mathematician Leonhard Euler described for the sphere in the 18th century. Euler discovered that all movements of areas on a spherical surface can be viewed as rotations. Here we see an area on a sphere that is now moved on the surface of the sphere around the axis of rotation seen above. No matter how you move the area on the sphere, you can always find an axis of rotation around which the area was moved, like here, clockwise around this axis of rotation. The grid we see here is not the grid we know from Earth, which we need to determine our positions, that means longitude and latitude. It is a grid that belongs to exactly this axis of rotation and only to this one. If you were to move the same area in a different direction, we would get a completely different axis of rotation, and the orientation of the grid would also be completely different. The pole of rotation is also known as the Euler pole, named after the famous mathematician which I just mentioned. This is all getting interesting now for plate tectonics when we consider two plates that move in different directions. Euler's considerations are very helpful for this. We can simply view the plates as the areas on the surface of the sphere. Let's first look at this using a very simplified system with just two plates. The two plates each comprise half a sphere and they move in opposite directions to each other. As we see it now with the two arrows, it seems clear that a gap is forming between the two plates. This would be a spreading zone. Plate A moves to the right, plate B to the left. But if we continue to follow this movement up and down along the black line, we come to a point where this is no longer valid. The plates, which represent hemispheres, have to remain on the surface of the sphere. Anything else makes no sense. Here we see how the plates move apart and how they move towards each other on the other side of the pole of rotation. The same area that covers the gap that is created here by the divergent moving of the two plates must be removed on the other side of the sphere, and that happens by thrusting them on top of each other. This is exactly the principle behind it. If spreading zones open up in one place, there must be a removal somewhere else. That means the formation of a subduction zone. With this, the basic condition that the sphere must always remain completely covered with areas, or in terms of plate tectonics, with lithospheric plates, is fulfilled. And something else is important. The velocity of the plate movement varies. It is zero at the pole of rotation, because there the movement changes from extension to subduction or thrusting. The highest speed of plate movement is achieved at the so-called rotational equator. This means that plate movement velocities change systematically along the same plate boundary. These are the relative plate movement velocities, where I always look at the movement between two adjacent plates at a very specific point. For example, the Pacific plate is moving towards the Japanese northern island of Hokkaido, which lies on the Eurasian plate, at a speed of 9 cm per year. This value only applies there. If I go further north and stay in the same subduction zone between the Pacific and the Eurasian plates, it changes. And this change in speed is related to the rotational movement of the plates. Here we see a slightly more complicated two-plate model with the transform folds added as additional geometric elements, the principle of which I already explained in the previous video. They only extend from segment to segment, but not beyond that. At the corner points, the movement is transformed from a divergent, like here on the right, or convergent, like here on the left side of the picture, into a lateral movement. Here again, two plates move by rotating around an axis of rotation, according to Euler's principle. And here again, two adjacent plates that move in different directions on the sphere always have a common pole of rotation. It is important that this pole of rotation only applies to this pair of plates. So on Earth, with its many large and small plates, we have a large number of poles of rotation, depending on which pair of plates we are looking at. I would like to take this opportunity to point out very clearly that both the rotational equator and the rotational pole have nothing to do with the geographical equator and the north or south pole, which result from the rotational movement of the globe as a whole. This is a constructed reference system with pole and equator that only and exclusively applies to the two plates whose movement between each other I am currently looking at. So if I look at the South American and African plates, for example, then these two plates have a common pole of rotation, which is located at almost 60 degrees latitude near the southern tip of Greenland, and accordingly the associated rotation equator is 90 degrees away from it and is approximately 30 degrees south of the geographic equator. I will come back to this later again in connection with the geometric orientation of transform folds. This figure shows a system of three plates that all move against each other. Of course, all movements are again rotations, namely around the rotation axis, which only apply to one pair of plates. So, for example, the green plate C moves away from the red plate B down here. On the other side of the rotation pole, there is a subduction zone. And it's the same between the blue plates A and B up here. On the left is a spreading zone, and on the other side of the rotation pole, there is a subduction zone. You can see here that the individual plate boundaries can be aligned very differently, but they still belong to a common system. And you see that somehow all the plates on Earth are related to each other in this way. And when there are major changes in the direction of plate movement, such as the collision between India and Eurasia over 40 million years ago, then the geometric effects can be noticed across the entire Earth. I'll come back to this later when I look at the submarine volcanic chains that form over hotspots. For the moment, that should be enough about the geometric relationships between the plates. This time, thank you for listening, and I'll be happy if you stick around, and I recommend continuing with the video on triple junctions.